We're now going to examine ideal versus non-ideal gas behavior. This information in Chem 2A is found in section 8.1 and in Chem 22 in sections 11.2 and 11.8. The points of the kinetic molecular theory of gases apply perfectly only to something called an ideal gas, as in ideal gas law. So what is an ideal gas? Well, an ideal gas is a hypothetical gas. It doesn't exist. It is in the same category as what we would refer to as an ideal man or an ideal woman. Right? We know these are hypothetical constructs. They don't exist. Only real men and real women exist, and only real gases exist. But real men and real women can approach ideal behavior, we've seen that, under certain circumstances, but they can deviate or veer off from ideal behavior under other circumstances. The same applies to real gases. Only real gases exist in nature. Under certain conditions, real gases will demonstrate ideal behavior. But under other conditions, a real gas will be stressed. And then we're going to see deviation, a veering off from ideal gas behavior. So what that means is that the gas is no longer behaving strictly according to the kinetic molecular theory. So the calculations we do using all of the gas laws, the answers that we get from those, if a gas is stressed under certain conditions, those calculations will correlate less and less with what that gas is actually doing under those stress conditions. In fact, if you stress a real gas enough by experimental conditions, it will liquefy. It'll turn into a liquid. It won't be a gas anymore. And then the points of the kinetic molecular theory won't even apply at all. And none of the calculations that we do using gas laws are valid. So points of the kinetic molecular theory, calculations involving gas laws do not apply to liquids and solids, do not describe matter accurately in those states. Interestingly, an ideal gas, which of course is a hypothetical gas, can never be liquefied. All real gases can. So what are the conditions with which we would observe ideal gas behavior, and why? In a nutshell, I just highlighted it in red here. Conditions necessary for a gas to behave very much like an ideal gas are when the pressure of the gas is low and the temperature of the gas is high. And why is that? Well, if the pressure is low, right, and according to Boyle's law, low pressure correlates with high volume, large volume, right? If the volume is large and the pressure is low, that means gas molecules have lots of room to move around. If that's the case, then most of the space occupied by the gas is empty space, and the gas particle size itself is very small or negligible. We can ignore it compared to the container volume. So when we do gas law calculations, we just plug in the volume of the container without taking into consideration that small amount of space that's being occupied by the gas molecules themselves, right? They can't move around in a space that's being taken up by the volume of another gas molecule. But if we assume that the gas particle size is small and we can just ignore it, then we do calculations assuming the free volume to move is the container volume itself. And as long as there is a big volume for gas molecules to move around in, that's a good assumption. Those conditions are ideal conditions for real gases, and they will correlate well with the behavior of an ideal gas. Right? If the temperature is high, well, we know that temperature is directly proportional to kinetic energy on average in Kelvin. So at high temperature, the interactions, specifically the intermolecular forces of attraction between gas particles, is small. Again, can be ignored because they have such high speeds on average. They're moving so fast. Therefore, collisions between gases are perfectly elastic, meaning when they collide together, they just bounce off. Energy can be transferred between them, but it's never lost or gained overall in the system. It's like these perfectly elastic conditions. Or perfectly elastic collisions, I should say. So the gas molecules collide, bounce off, no energy is lost, and the system remains in the gas state. It would be like a pool table where when you hit the cue ball and it moves and collides with other balls, they just keep moving indefinitely, right? That does not happen in the real world because energy is lost in the collisions. But with gases under high temperature, the collisions are perfectly elastic. The gas molecules just collide together, bounce off, and that system remains stable indefinitely under high temperature and low pressure conditions. But what happens if you stress a gas? If you change the experimental conditions and stress a gas by increasing the pressure, lowering the volume, and decreasing the temperature, now you're going to see that a gas starts deviating from the points of the kinetic molecular theory and displaying non-ideal gas behavior. So what's happening under high pressure conditions? We decrease the volume to achieve high pressure conditions. So the gas particles are crowded. If they're crowded together, there's no longer lots of empty space, and the gas particle size themselves becomes significant compared to the container volume. You can no longer ignore them, right? So that means that gases aren't free to move around in the container volume because there's lots of other gas molecules taking up space, right? Because the volume is small and we have crowded conditions. Also, low temperature, and let's put that arrow down here. Both of these are needed to truly stress a gas. At low temperature conditions, the interactions, or the intermolecular forces of attraction between gas molecules become significant. That's because they're moving more slowly. Kinetic energy on average has dropped because the temperature has dropped and their average speed or velocity has decreased. Now collisions between gas molecules are no longer perfectly elastic. These interactions are becoming observable and significant. When gas molecules collide, some energy is lost because they have interactions that are now significant or observable. They lose energy as they pull apart from each other, and you start seeing the gas deviate more and more from the conditions necessary for ideal behavior when you increase the pressure and decrease the temperature.